Okay, here we go, finishing up notes part 1, where we have this example of a marshmallow that's being launched with some speed at some angle, and we're going to figure out how high does it go, how long is it in the air, and how far does it go. So, how high does it go, this distance, how long is it in the air, that amount of time, and how far does it go, so that amount of distance. Now, take a look at what I've done here right off the bat. Is I am finding its vertical and horizontal components of velocity, we say. So all we're doing here is we're using what you learn in geometry, SOHCAHTOA, all right? So sine is the opposite over the hypotenuse, cosine is the adjacent over the hypotenuse, tangent is opposite over adjacent. That's an A right there. And so if you set it up, here we have a right triangle where the velocity is the hypotenuse, and this is our angle with respect to horizontal, remember? So if we were solving for this side, which is horizontal velocity, labeled v sub x, we could say, I'll show this to you once. So we would be using cosine, and we'd say that the cosine of the 50-degree angle is equal to the adjacent over the hypotenuse. So the adjacent over the hypotenuse, and in solving for that we could multiply both sides by 8, and we would get 8 times cosine of 50 degrees equals the horizontal component of velocity. So you can do the same thing for the vertical using sine, and we end up with this. So there's our vertical component, and here's our horizontal component of velocity. Notice two things. One is I'm using a bunch of decimal places because this is not a final answer. This is within calculations. And also, they don't add up to 8. Okay, this is a Pythagorean theorem thing, not a this plus this equals this. Okay, so given that, we can then solve, and I have that on the next pages. So, first of all, how high does it go? So here's my diagram. I know it has some initial vertical velocity, which is this. Notice how 8 is, we can forget about the 8. We're just interested in vertical motion. So the vertical component of velocity is this. We know acceleration is downward at negative 9.8 meters per second squared. And I say v equals 0 meters per second. So what we're using, the problem doesn't tell us this, but we know that at the top of its flight, its vertical velocity is 0. So that's implied information, and we're using it in our calculation. We want to know its position up here. Its initial position in the vertical direction was 0. It started on the ground. So notice how I've written all my given information. I've written what I want to know. I have a diagram. And then looking at this, it's pretty easy for me to select not this equation, but this one. Yeah. So substituting in, we end up with final velocity at the top, initial vertical velocity, acceleration in the vertical direction, final position, initial position, giving us 1.916 meters. And so looking back at what information is presented to us in the question, oops, where is that? I don't have it in front of me. In terms of, oh, let's see. So it looks like just one significant figure, so we'd actually have to round that to, that's x equals 2 meters, based off that. Okay, how high does it go? That was that one. How long is it in the air? So notice again how I have written out, I have a diagram. We're looking for time here. How long is it in the air? I'm showing you some additional information in this. The question is asking us what's time here. We know the acceleration is negative 9.8 meters per second squared. There's some initial vertical velocity. So again, we're totally disregarding any horizontal motion. Totally disregarding. To answer this question, we're actually doing this. I'll show you this afterwards because it's useful information. But essentially, based on the information that we wrote above as well, so final position is 0. I should have written this out separately, but final position would be 0. That's a vertical position, back on the ground. Initial position, 0. Initial vertical velocity, like before. Time, we don't know. Acceleration, negative 9.8. And time, we don't know. So this is the kind where you end up with t in two locations, and we have a t squared and a t. So I am setting it equal to 0 and factoring, and this gives us two answers. One is t equals 0, and one is t equals 1.25 seconds. Notice how that makes sense, because when the, whatever this is, a ball started, that was at t equals 0, and when it landed, that was at t equals 1.25. Whoa! So we get two answers, and they both make sense in this case. This would be the start, and this would be the finish when it lands on the ground. Okay. So what is this additional information? Frequently finding time to max height is very helpful. We didn't need it for this question, but just using the vertical motion. So we know our final velocity at the top of the flight is 0, and the initial vertical velocity and acceleration and time. So we can solve for the time to maximum height, and that's helpful. I'm going to use this. That's helpful in calculations. So that would be the time right here. Notice how the time in the air is twice the time, that's twice. Notice how the time in the air is twice the time to maximum height. So if it takes that much time to get up here, it's going to take the same amount of time for it to get back down to its original height. Interesting. Lastly, how far does it go? So this is sometimes referred to as the range. It is the horizontal displacement, or the distance it travels in the horizontal direction. So here we're finally using this v sub x, the horizontal component of the velocity. And horizontal motion, we can disregard the fact that it's moving up and down. So this, whatever it is this ball is going to have a constant horizontal velocity. Is that always true? Yes, that is always true. And so if it has a constant velocity, we don't even have to pay attention to, we don't even have to pay attention to the 1/2 at squared term. It's just distance equals velocity times time. It's starting, we say, at an initial position of 0. So here's our horizontal velocity. This is the time we got for time in the air, meaning time to get over here, and we multiply and we get 6.4 meters. That would be the range, the horizontal distance traveled, or how far does it go. Same thing. Thanks.